it says next. All right. Well, I want to talk about a couple projects that transportation agencies have been willing to fund through the competitive grant process that have involved a significant component of using UAVs. So this is what these agencies have seen worth funding and where they see some of this technology going, working with applied researchers such as myself. So the first project I want to talk about is one funded by U.S. Department of Transportation out of their Commercial Remote Sensing and Spatial Information Program, which was under the old Safety Blue Act from a few years ago. And USDOT felt that unpaved road networks were under-assessed and that remote sensing technologies could help provide data useful to road managers in making decisions on using the road repair dollars wisely. And I've got quite a team on this. So really we're talking about developing an unpaved road assessment system that could be deployed rapidly and inexpensively. So if you're a gravel or a dirt road manager, what do you care about? Well, you care about how wide the road is, whether the crown is sufficient because you need water to run off the road. You want to know how many potholes there are and how bad they are. You want to know if there are ruts there. You want to know if there's corrugation or washboarding, if there's presence of drainage or a reverse rut, a float aggregate berm. Now, our challenge here is that, frankly, when doing with gravel and dirt road management, is our competition is the guy driving down the highway and eyeballing it and saying, that looks bad. Or the person calling up and going, the road is bad and my son can't get, the school bus can't get to my house in a rural area. So there may be a requirement, a need for high-resolution data, supposedly, but there's still that challenge of competing with the eyeball surveys. What we use as our index was something called the Unsurfaced Road Condition Index, developed by the Army in the 1980s, and this uses both the density and severity of distresses, as they call them in the manual, on the roads, and use those distress data to manage the road repair. So, equipment platforms. I'm going to skip straight into the technical stuff here. So the first year we went out and flew a Bergen Taser 800 single rotor helicopter, and it did what we needed. Frankly, I'm not that fond of single rotor platforms because the interaction between a person and that carbon fiber tip blade is not something I'm eager to see. So in the second year, we switched to a Bergen hexacopter. It's a folding one, so it fits in the back of a Prius or your pickup truck or whatever you may be driving out to the field. It's made in Michigan. That does us no harm when bidding projects in the Midwest and job support. And that's an important part of things to consider. Flight up to 30 minutes, and with this group, I'll say 20. And 4 kilograms, yeah, we're usually flying at 2 to 3 kilograms at most. But the nice thing about this payload is we went to flying a digital SLR, a Nikon D800, we've got an 810 as well. So full-size sensor, 36 megapixels, up to 4 frames per second, $3,000 off of B&H or Amazon, and that's an awful lot of pixels to get for that price in the air. So let's go straight to some demonstration imagery here. This was a demonstration we did in South Dakota last year to local and state road managers, so people that work for county road agencies, county road commissions. They're concerned with, how deep is it, how bad is that ditch? Interesting, I showed this to them, and they immediately got into sufficiency of turn radius for large vehicles and automating that calculation. That was something that they saw out of these data that I had not originally thought about. I thought I was just counting potholes. Knowing where the areas have washed out after a storm. Again, picture, I'm not going to go all the way to 2030, but we'll be able to fly beyond line of sight, and if you're out in the places like the upper Midwest and the Great Plains states, you've got miles of roads, almost no trees by them, they're in township, range, and section layouts, so you could get your UAV out there and fly many miles of roads. We're not at that point yet, but again, the future is coming, as Kevin was saying. And again, we're flying here about 25 to 30 meters height. And so we're getting on the order of millimeter scale resolution, which may be overkill, But if you're trying to classify your potholes into sub 1-inch bins, I'll take all the pixels I can get. So this year we went out and did a demonstration in Kansas to, again, our real audience here is local county road commissions. Rural roads are generally not responsible of the state, so your state DOT is not your end user for this. The other end users here are groups that care a lot about whether their road is passable that week. So think haul roads, mining, dairies, quarries, those sorts of things where, you know, if it's not passable and your only way out to get your product to market is a 20-mile road from the mine, then flying up and down your unsurfaced road is not such a crazy idea as might appear to the local road commissioner who just wants to send his guy out in a pickup truck. So, you know, here we're flying about 25 meters over an intersection with some pretty severe problems in terms of rutting. We picked this site to do our demo in Kansas, and they graded it in the morning we were going to go do our demo. So we showed them the 3D process data and said it used to look bad. And here's the group we presented to out there. Again, there's the Bergen, and then we took out a little 3D robotics Iris Plus as well, just to show the idea of rapid aerial imaging as well. So you've created 3D data. As we've learned, all this 3D data processing is going to go to the cloud, and all the photographers, we have jobs. According to Kevin there. So you've got your 3D data. What do you do with it? And it's really this is where we come in as applied researchers. It's not just creating a 3D model; it's automating the extraction of useful information out of it. And in our case, it's those distresses, the potholes in severity categories. You know, the amount of crown in categories is better than 1%. Where the worst parts of the ruts. So you create here. This is a 3D point cloud. We actually created so the commercial photogrammetric close-range photogrammetric software mostly uses structure from motion as its underlying algorithm. Those algorithms are actually available online, so our engineers liking to turn every single possible knob went and downloaded the ASFM algorithms and created our own 3D processing software. But that uses but we also use Agisoft PhotoScan as well when we don't want to have to turn every knob. So that was created with our own structure from motion software glued together. DEM here, the important thing is in terms of you get to ask questions of accuracy. So those traffic cones in the background are 75 centimeters tall. You can actually see them on the far left there as little orange peaks. We were within 1 centimeter, a little better than 1 centimeter in our reconstruction of the traffic cones. That helped convince the people we were showing this to that we were actually getting good 3D data out of this. An exaggerated height profile, so you can see the potholes in there. In other words, you do have a chance of detecting them. And then really, so this is where we come in. It's those automated detection algorithms that are niches in terms of staying employed. Keep thinking about Kevin's presentation. So automated detection of potholes, like my text written there, using a couple different algorithms. Automated detection of washboarding, and then also the ability to define what is the road and throw out what is not washboarding. Setting minimum detection areas, so if it's a very small area, saying I'm not concerned about that. Because what we really found is we were finding when we did this, compared this to ground truth data, we were finding every single distress that the field person would have had to sit there and measure with a ruler piece by piece. So we were like a surveyor doing, we were like a field crew measuring every single part of the road possible. So potholes, we got 96% correct. Crown damage, we were doing then plus or minus 1%. We still need to improve some of our rut detection and corrugation detection work there. But that being researchers, that's why you go out and find the next applied research grant. And then again, you've done automated detection of problems. Now you need to do something with the data. So we integrate this into the RoadSoft GIS decision support system, designed for managing paved roads, but unpaved, the data works in there just as well. In full disclosure, this is developed by a colleague of mine at MichiganTech who is soft money funded like myself, so he's pretty aggressive in terms of making his sponsors happy. And then costs. Manual methods, if you compare them to things that get the same amount of detail, range from somewhere between $30 and $160 a mile. Pazer doesn't get as much data, so that's not really comparable. That's closer to windshield surveys. When I first did the calculations for this, using our hexacopter-based system, and I came out with about $20 a mile, and I was a little impressed by that. But then the URCI, the Unsurfaced Road Condition Index, uses the principle of representative road segments. So you can get a couple of 100-foot or 30-meter segments per mile of road, and that represents the larger road network. And if you can do that and deploy it rapidly, then all of a sudden you're very cost competitive and you can get below $1 a mile. And that's assuming 8 hours a day, 3 days a week, 21-week data collection season for doing 300 real road miles. So we're talking about some significant data collection. So that's that project. I see I've got 7 minutes and 21 seconds, 20 seconds, 19. Okay, I'll keep going here. This is so that's a USDOT perspective trying to push forward remote sensing in a particular area. What does a state DOT see in how these technologies could be used? Well, they put out a competitive grant, we bid for it, and after much discussion, these are the applications that Michigan DOT and MDOT expressed interest in. So they want us to look at roadway assets, confined space inspection, which caught me by surprise. I hadn't anticipated doing that. Monitoring traffic, looking at optical and thermal IR for bridge inspections. Kevin showed some bridge inspection work there. Our bridges aren't 500 years old, although they seem like it in Michigan. And then also doing some LIDAR deployment from UAV as well. So we looked at multiple platforms. Again, the Rd Hexacopter is our workhorse. It's folding as well. Pretty good payload. We did some underside of bridge imaging. You don't have to have that upside down cherry picker, for example. So confined space inspection. I said I didn't want to do this originally. I said just stick a drop camera down in there. And the folks from MDOT, from Michigan DOT, said, no, you don't understand me. This is what you need to do to win the project, to be awarded the project. I said, this is a great idea. I would love to do confined space inspection. So we flew in through the entry hatch, which you can kind of see there in the bottom middle one. And we actually ended up using a toy one that sent live video via Wi-Fi to our phone sitting at the entrance hatch, and that was good enough for the proof of concept. They wanted to be able to see around and see if it was safe to send a person in there. Right now, they have to send a person in to see if it's safe to send a person in there. They would like us to do some dangerous gas detection, carbon monoxide, hydrogen sulfide as well. There are small sensors that you can do that with. They're going to put out a second call for proposals, and none of you want to compete with me on that. We also did a demonstration to crash scene investigation. The local police folks at MDOT found out about this project. So I got to watch a police car come peeling in, leaving skid marks and behind the police station, which was kind of cool. They put out their standard reflectors. They usually measure the distances with a laser rangefinder. We flew overhead. Again, 36 megapixels with our Nikon D800. And the ground sample distance on this was 2 millimeters, and the police guy took it through a standard crash scene investigation, and it was more than satisfactory. And the state police were there as well, and then they went out and bought a $150,000 Ariane Scout, which is a great system, but they maybe should have worked with us a little more too. But anyway, I'm glad we made that convincing case. So thank you, Ariane people. I'd take a free one. We also did traffic monitoring. We did briefly talk about tethered multi-rotors, but really the direction we went in this was a traffic monitoring blimp. And I know there are commercial systems out there as well. A blimp in a box will sell you one for $160,000 with a complete system. I'm a university researcher. I do not get $160,000 for my hardware to demonstrate this to DOTs. I bought an $800 advertising blimp. The helium ended up costing almost as much as the blimp did. I bought a $300 gimbal and a $400 Samsung Galaxy camera. So it looks like a regular point and shoot, but it has a 4G chip built into it. So for $1,500, here I am on the bottom right, streaming in the top left of the image there. streaming near live video into a mini traffic operations center during the ITS World Congress, Intelligent Transportation Systems, all that connected vehicle stuff we were just hearing about. And, you know, 12,000 people and all that. And it worked, and this was more than convincing enough to make our Michigan DOT sponsor happy, and hopefully let us do the next phase grant with them. And State of Ohio did go out and purchase, again, after hearing about this, the lump in the box system, so it just cost 100 times what our demonstration did. I'm glad they could. I no doubt it's more capable than our home built system. We also did bridge detection evaluation. I'm running out of time here, so again, here's a couple alternatives on the right to avoiding that underground cherry picker. We had a 7-mile stretch of interstate in southeast Michigan that was closed for reconstruction, so I didn't have to worry about traffic going underneath. We could cooperate with the number of vehicles that were there, the tiny number of vehicles that were there for construction, and the bridges were closed or we went over them. Eventually we'll be able to do this without the bridges being closed, but right now this is what it takes. So we got all kinds of data, bridge condition data, automated detection of the potholes, did thermal evaluation, thermal analysis to find those delaminations, so that's where the concrete has begun to debond, but it doesn't look like anything at the surface, but there's an air gap that creates warmer areas. So you do automated detection without having to necessarily do coring in the bridge. The alternatives here are something like chain drag. Actually, the picture at the top left is what MDOT ended up sending around to all their management. Like, we could do construction site monitoring of this with just a few minutes flight. And frankly, I did the one at the top left with my Phantom 2. That ability to do construction site monitoring is really what helped sell the technology to many of the senior people, because they did actually fly this a couple days later with a manned helicopter. My imagery is just as good. We did some UAV-based LIDAR. We used a small Clio LIDAR. They're not really designed for using UAVs, but that's one of the things you get to do at university research is push those capabilities. And we got good reconstruction there, solved some problems with localization and mapping. 2.5mm orthophoto with that 36 megapixel camera at 25 meters in the air, so pretty good resolution there. Combined it with the thermal data and did the automated detection of where the delaminations were. You get to use cool words like delaminations when you do bridge condition assessments. And as I said, we did those demos during the ITS World Congress, including emergency response scenario. And there you go.